All right, so I want to talk about exospheric signatures of water, of the water interaction with the surface of the moon. And this is work that has been supported by Survey as well as through LRO and LADI. So the big questions that we have outstanding in terms of understanding the water cycle on the moon include things like, what are the characteristics of the diurnal hydration on the daylit surface of the moon? And what are the relative contributions of different sources, including solar wind, meteoroids, to the water on the moon? And then also, we still have the question, does water migrate from lower latitudes to the permanently shadowed regions? And then, what is the relationship between these ongoing processes and any ancient deposits that exist in the polar permanently shadowed regions? And since some of you may have flights to catch, I'll give you the answer real quick, that if we have really good measurements of water in the exosphere of the moon, we can start to address some of these questions. So exospheric water measurements can tell us what the source of water to the ongoing processes is, can tell us what that source rate is. We can also learn about the physics of the interaction between water and the regolith. And then it can also tell us about the efficiency of migration to the cold traps. So what I'm going to show today is modeling, and this is the Monte Carlo model that follows the motion of particles under gravity. There's no collisions or radiation pressure, and what I vary in the model are the sources. So I use the model to simulate a solar wind source, and I also can use the model to simulate a meteoroid source. And then the other thing that we can vary in the model is that the surface interaction. What is the energy, the activation energy of desorption of the molecules from the surface? But the things that I do not vary in terms of that surface interaction is I assume everything completely thermalizes on contact, and that the re-release of the particles have a velocity taken from a Maxwell-Boltzmann distribution at that local surface temperature. And then the loss processes that we include in the model are just any particle that goes further than 35 our moon away is considered gone, and photolysis, and then any particle that lands in a permanently shadowed region is also removed from the model. So the first simulation that I want to show you is our one-hop simulation. So this is a simulation that assumes that after a water molecule is released, it goes through the exosphere. It comes back to, if it makes it back to the surface without being lost, that it is not allowed to be re-released again. And this is in case that interaction with the surface, the water molecule dissociates and is not able to reassemble as a water molecule to get re-released. So this is what the exosphere looks like in that case. We have, as a function of local time, we have noon here. So here's dawn, and here's dusk. And this is latitude from the equator to the pole. And so if meteoroids are the source of water to the exosphere, you have your densest water measurements near the equator and in the morning hemisphere. So the source is centered on dawn. If solar wind is your source and you have a prompt release of water from the interaction of the solar wind with the surface, your distribution is centered at noon at the equator and falls off as you go away from that subsolar point. And here the scale is the water density at 50 kilometers altitude, which is where the NMS on LADI was measuring water. And the LADI observations have placed an upper limit on the density of water averaged in this entire equatorial zone, because we don't have spatial resolution with these LADI data. That's the upper limit outside of the strong meteoroid streams is 1 water molecule per cubic centimeter. So I've scaled these to get it so that you have that average value here in this region. And so for meteoroids, the source rate to reproduce that density is 0.3 grams per second of water released into the exosphere, which is less than 1% of the inventory of water coming in from meteoroids. For solar wind, it's even a smaller percent of the total inventory. It's less than a fraction of a percent of the amount of hydrogen that's delivered to the moon being converted into water to reproduce that upper limit from LADI. And then this is looking at that same model in a different way. This is taking that equatorial region and looking at it in as a function of local time for different combinations of having solar wind and meteoroid sources. So if both of those sources are acting, you would have a very different local time structure of your water exosphere. So in this way, if we have data that can resolve in local time, even really coarse 4-hour local time bins, you can separate out the amount of or contribution from solar wind or meteoroids according to this model. Okay, so that's if water molecules do not migrate on the surface. They take one hop and they're done. However, if they do multiple hops, then we have a different looking exosphere. So here, just for reminding you, was the one hop model. Here's where you allow molecules to hop around until photolysis or landing in a cold trap or escape removes them. And you can see that for the meteoroid source and for the solar wind source, you don't have, you have the same spatial distribution. They all have a peak at dawn. So you can't use this now to separate out the local time distribution does not separate out your difference between a meteoroid source or a solar wind source. But what you can do if water does migrate in the exosphere is use this to understand the surface interactions. So if I vary the stickiness of the surface, like what the activation energy is for that water molecule to leave, it changes the position of the peak. So here, this top is where water has a much higher activation, more or over 1 EV, which reproduces a peak in exospheres where the water's leaving the surface close in the local time to where the lamp observations show the dip out in the absorbed water on the surface. But if it's a lower activation energy, some of the values that some of the laboratory experiments give you, you would expect the peak to be more over at dawn. And you also have a latitudinal effect that you could look for to verify that that's what's going on. And yeah, so this is what I was saying, that the LAMP data that Amanda was talking about show this desorption of water at local times, close to noon. So that's consistent in our model with being a much higher activation energy. So I said that the local time distribution when you have migration does not reflect the source anymore, so you couldn't use that to tell if it's coming from the solar wind or from meteoroids. But what you can use is the passage of the magnetotail to help differentiate how much of water in your exosphere is coming from the solar wind versus meteoroids. So these are some different runs that show what you would expect that local time profile to be if you have, when you consider the magnetotail passage. So the set of red and green and purple and yellow here are for the same activation energy of the surface, but different phases of the moon. And then here again, it depends on if that solar wind is promptly coming out in the interaction and doesn't account for any sort of delay in that. But you can see that you get a much faster fall off with local time at full moon compared to at new moon due to the drop in the solar wind flux as the moon goes through the Earth's magnetotail. But both of those look very different than the situation where everything sticks to the surface of the moon and you're just seeing the solar wind without migration. All right, I think I'm done, actually. Yeah, so in conclusion, if we get spatially resolved measurements of water in the exosphere of the moon, we can use that to learn a lot about the water cycle on the moon. For example, does migration occur in the exosphere? Well, if we see that the spatial distribution and local time has some peak at a specific local time and a matching latitude profile, that will give us a very good measure of what that activation energy is for release of water into the exosphere. And then the contributions of solar wind and meteoroids we can tease out based on the magnetotail passage or looking during meteoroid streams and that sort of thing. And and that will give us a lot of information about whether water is actively being added to the permanently shadowed regions. So, thank you.
Questions?
Hey, Dana.
Hey.
Did you say the upper limit was 1 molecule of water per cc?
That is in times outside of the meteoroid streams. So we see higher densities during the meteoroid streams, but in the times when we're not in meteoroid streams, there is an upper limit of 1 per cc, in the 10 to several tens of kilometers altitude range.
Yeah, that is a sensitivity that is extremely difficult to measure, even for the best mass spectrometers. So, yeah, it's good luck measuring that. That's all I was going to say.
I was wondering, when you're calculating these processes as the moon is passing through the magnetotail, are you considering magnetospheric ion sputtering?
I'm not. I'm just assuming that, you reduce the production to nothing. But, I guess OJ, it was an order of magnitude lower. Yeah, I could do that.
Hi, Dana.
Hey.
I was wondering if, looking at the meteoroid source in particular, another potential source that we've talked about being a potential contributor to this is degassing from volcanic material as well, especially when there's some disruption, some fault or something that happens. So I'm wondering if that would be lumped into the meteoroid source signal, or if you could separate those two, especially if there's an event that maybe we could detect with some future seismometer on the surface or something, if we could see a pulse of activity associated with that.
Yeah, I mean, that's a good question, and we should get together because I have no idea what the, variability of that source is and the spatial distribution, and if you can provide that for me, then I'll model it.
Yeah, thank you. I was wondering, and perhaps you answered this in your third bullet, but if there's the correlation between the space weather solar activity with the multiple hops or the skips, especially in the breakdown, of the hydrogen.
So say that one more time.
So if you notice a solar burst coming off the sun, is there a correlation between when it reaches the moon and the event for the?
Okay, so no, we haven't seen that. But what we do see is that, for example, with helium in the exosphere, that responds very strongly to the helium in the solar wind. And we can see the helium exosphere go up, and when there's some event that's either a CME or something heavy in helium, and then we see the helium drop out during the magnetotail. We really don't have great, a whole lot of data on from Laddie. We have a total of like a couple hundred measurements of water. So, and there weren't any big solar events, I don't think, during that mission.
I don't know. Yeah, that's what
Yeah,
I'm
I don't think there
wondering.
were.
Yeah. Okay, thanks.
So I was wondering, I think you mentioned that the water content somehow correlates with meteor showers.
Yes.
But the meteor showers, that's the tip of the iceberg. You are continuously hit by the sporadic background. It's 5 tons a day shoots rain down on the moon day and night. So I wonder if then in the water budget, that should be a lot more, serious contribution than just the stream particles or the.
Yeah, I mean, oh, wait, sorry. These numbers here are for the sporadics. So, yeah.
Okay, we need to move on. Okay, our